Hi, this video lecture, we're going to discuss confidence intervals. So again, we're now in this process of trying to do inference on our statistics. Again, basically, we're trying to take a sample and use it to describe a population. Well, the thing is, though, that when we take our sample from a population, it's only a small group. And it's really unlikely that that one small group is going to be perfectly representative of the entire population. And in fact, sometimes when you get your sample, it's going to be completely off. It'll just be completely wrong. That's just due to random chance. So that's going to happen every once in a while. And of course, we can do things to make this, well, happen less frequently. Things like making sure we have a big enough sample and a diverse enough sample. But no matter what, even if we're doing our jobs perfectly, because of random chance, there are going to be cases where we're just wrong. And there's really no way around that. The way we capture that uncertainty in statistics is with what's called a level of confidence and a margin of error. So what we're really doing when we conduct polls is we're finding what's called a point estimate. And again, that point estimate really is our sample. That point estimate is our sample statistic. And then what we're going to do with that point estimate is take what we know about probabilities and essentially the normal curve and try to combine these ideas together. So a quick note about confidence. Our level of confidence is going to be related to the variable alpha. So you see it's kind of looks like an A, it kind of looks like a fish to some people. That's our Greek letter for the lowercase alpha. And our level of confidence is very much related to alpha. Our level of confidence is going to be 1 minus alpha. So we're talking about complements here. And then we typically turn our confidence into a percentage. So it's really just complements. So if our level of confidence is 95%, then alpha is 0.05. Because, again, the complement of 95% is 5%. And so we just convert that into a decimal for alpha. If our level of confidence was 90%, well, the complement of 90% is 10%, so alpha would be 0.1. If we had 99% confidence, then alpha would be 1%, which is really 0.01. Now, if we have a normal curve that actually represents the true parameter as our mean, all right, so we have our normal curve, our peak is our true parameter, and I have 95% confidence. And what we mean when we have 95% confidence, it really means that 95% of the time, our point estimate or our statistic is going to be approximately 2 standard deviations away. That was our empirical rule. Now, instead of using approximately 2 standard deviations away, we're actually going to be a little bit more specific now in this chapter. And instead of saying approximately 2, we're actually going to be very specific and say that it is within 1.96 standard deviations. Now again, remember what that really means is that we measure standard deviations in terms of our z-scores. So our z-score would have to be 1.96. And we call that z-score also the critical value. So yeah, what's going on visually is if we have the data, and this is our true parameter. Now, the thing to kind of keep in mind is that our true parameter is often not really known. We don't really know how every American feels about a certain topic because we've never asked every single American. We haven't asked hundreds of millions of people how they feel about things and recorded the answers to every single one. Now, that doesn't mean that this information doesn't exist. It does. Essentially, every American would have an opinion, one way or the other. Yes, no, or even I don't know. So this exists before we do any polling. And our goal is that hopefully our sample is going to kind of represent this. But remember, that idea behind that empirical rule and the normal curve is that if I have 95% confidence, that means what I'm really saying is that in the middle, I have an area of 0.95. All right, and that's my range between 1.96 standard deviations away on either side. Now, as we said before, if I have 95% confidence, that means my area is 0.95, so alpha is going to be 0.05. And what we do is we have to divide that by 2 for our two different tails. Again, if there's 95% inside, there's 5% outside, and we split that 5% up into our left tail and into our right tail. So let's actually take a look at an example from last year, June 2019. Gallup polling polled 1,015 adults in America and asked them, do you believe that higher education is affordable? 274 of those people surveyed responded that they do believe that higher education in America is affordable. So it's always a good idea with any type of example to, again, take that paragraph of information and try to summarize it into just a few important numbers and kind of denote our variables. So if they polled 1,015 Americans, well, that's my sample size. My sample size N is, well, 1,015. We know that 274 responded that they do believe it's affordable. So we'll let that be our X, which stands for successes. One of the most critical things to do when it comes to these types of problems is to then make sure, once we're kind of looking at this raw data, what kind of data is it? Am I looking at a proportion, which is that qualitative? Did people answer yes or no? Or am I looking at quantitative, numbers? Are people giving me a number as an answer? Well, in this case, they're answering yes or no, so this is absolutely going to be a proportion. We're dealing with a sample proportion. And our notation for our sample proportion is p hat. And then we've been doing probabilities, so hopefully this feels pretty familiar. We divide our successes, 274, by our sample size, 1,015, and we get this big long decimal. I'm going to be rounding things to roughly 3 decimal places during our examples. So if I round that to 3 decimal places, I get 0.27 as my sample proportion. And again, this is just taking the raw data from the problem. We haven't really started doing anything with this problem yet. So that's because our goal is to take that sample proportion and to come up with some sort of statement at the end that can describe how our entire country feels about the affordability of higher ed, with the knowledge that if we had asked a different group of 1,000 Americans, we're going to get a different percentage. You know, it's very unlikely that if we asked a different group of 1,015 Americans that exactly 274 would say yes to that question. We're probably going to get a different number. So how do we take into account that variability? Well, the first thing we should always do is just verify that our data is going to be independent and approximately normal. Now, this is absolutely a critical first step in every type of actual statistical research. My stat lab's not going to necessarily make you do this step every single time, because they're going to make sure the data is typically independent and approximately normal, because otherwise, what's the point? But you should get in the habit of just kind of thinking about these things anyway. So for independence, remember, independence means that my sample has to be less than 5% of the population. And clearly here, 1,000 Americans is definitely less than 5% of the population. Then I need to figure out if it's going to be approximately normal. And if you remember back to Chapter 8, whether it's going to be approximately normal, well, my criteria is different for proportions and different for means. So again, that beginning thing, before we even started really doing the problem, and we made sure that we knew that we were dealing with proportions, is going to be really important for this approximately normal part. Because for proportions, we know it's going to be approximately normal if it satisfies the n times p times 1 minus p, and it ends up being bigger than or equal to 10. Well, if we just plug everything in N being 1015, P is 0.27. We plug it in, follow the order of operations, simplify it on our calculator, we get 200.06. And is that bigger than 10? Well, clearly. So we can check off that it's approximately normal, and we can check off that it is independent, which means we can continue on with our statistical analysis. The next thing we want to do is find what's called the margin of error, and that's going to be based on our confidence level and the standard error. So we kind of talked about this just a minute ago. If I want 95% confidence, which is typically the standard, typically 95% confidence is the accepted standard for studies like this, then we know that we want to consider data that's 1.96 standard deviations from that mean, which means that's my z-score or my critical value. So again, what's going on? 95% confidence means my alpha is 0.05, and then my z-score, and again, z of 0.05 over 2, which again, remember, we're always dividing by 2 for the two tails. That gives us our z-score or our critical value of 1.96. And all of that was, again, kind of just given to us at this point. The next part is to, well, find out what my standard error is going to be. Now, if you remember from chapter 8, our standard error is our standard deviation that gets changed a little bit because we're now looking at a sample. All right, we're basically scaling our standard deviation based on the size of our sample. And again, this is the formula that we were shown in chapter 8, and it's really just a matter of plugging in the numbers in the right spots. We know P is 0.27, we know N is 1015, and if we plug that in and do our order of operations correctly, we should end up with 0.0139 as our standard error. Now, this is going to be a really important value. We're going to use this in just a second. Make sure you're taking the time to pause the video and check to make sure you're getting the same number I am when you're using your calculator. And most of the errors from this section are going to come from just not doing things in the calculator the right way. And I've mentioned this in the last video, your calculator is incredibly useful, but the problem is it's not going to do what you want it to do. It's only going to do what you tell it to do based on how your calculator understands the order of operations. So you're going to have to figure out how to use that tool effectively and make sure you're typing these in the right way. And so if you need to go slowly, do it one step at a time, that's fine. But just make sure that you can use your calculator. The other part of the errors are typically rounding errors. And again, if you come up with a rounding error where you're really close, but you're off by one of the decimal points, let me know by clicking Ask My Instructor and I'll fix it for you. Now, the margin of error, which is the next part, is multiplying that z-score we found in the beginning times the standard error we found in that last step. All right? It's just, again, the z-score times your standard error. So we multiply our z-score, which is 1.96. We multiply times our standard error, which we just found is that 0.0139. And then my margin of error is this guy, the 0.0273. That's my margin of error, and our margin of error is typically given by the variable E. Now the confidence interval. So the confidence interval is where we say, all right, we found our point estimate, right? We found that p hat to be 0.27. Our confidence interval means we take our margin of error and we go to either side of our point estimate, however big that margin of error is. So it's our point estimate, in this case, p hat. And then what we do is we subtract our error and then add our error to that point estimate. So we go on either side. So again, 0.27 minus 0.0273, and then 0.27 plus 0.0273. And we get our two answers. And this is our confidence interval. We have our lower bound and our upper bound for our confidence interval. And now we're up to the last step. I just have to write a conclusion. Now, there are several ways that you can do this in a professional setting, and we'll talk about, well, what we absolutely need to include. So the first way we can write this is we say with 95% confidence, and you always want to include your confidence level in your conclusion. The proportion of Americans who believe higher education is affordable is between, well, my lower and my upper bounds, that 0.2427 or 0.2927. And that proportion is somewhere between those two bounds. Now, what you're going to see a lot of times if you actually read this on social media or on the news is that what they're going to do is turn those proportions into percentages. Because again, percentages just make more intuitive sense to us as people. So we would say with 95% confidence, and again we want to include that confidence level, that the percentage of Americans who believe higher education is affordable is somewhere between 24.27% and 29.73%. And again, that just gives us a better intuitive idea of where these numbers actually lie. The other way we could write our conclusion is using our point estimate and the margin of error. So with 95% confidence, the proportion of Americans who believe higher education is affordable is the 0.27. That was our point estimate. And then we just include our margin of error at the end. And our margin of error would be 0.0273. And similarly, a lot of times you'll see that converted to percentages because they're just more comfortable for us to deal with. So with 95% confidence, the percentage of Americans who believe higher education is affordable is 27%, but we do have a margin of error of 2.73%. So the confidence part. The really, really important piece of information to remember is that we have no idea, and we never will, if our point estimate is accurate. And that's going to be true for any study you do or any study that you ever see anywhere, online, in the news, on social media. You will never, ever know whether or not that point estimate is accurate. The true parameter is going to remain unknown because it is impossible or impractical to ask every single member of a population to answer a question and to record all those results. So keep that in mind that, again, it's all kind of made up just a little bit. And what we mean by that confidence level, though, is that if I say I have 95% confidence, that means that 95% of the time, my sample is accurate. My confidence then is in the method, not the result. So what I'm saying is that I'm confident that 95% of the time, my answer will be reasonable. That also means that 5% of the time it is not reasonable. And we have no idea which one it is. There is no way to distinguish which one is accurate and which is not based on just doing a confidence interval. Our confidence is in that method. So let's talk about what that method's really saying. So our true parameter is P. So my normal curve here, this normal curve in blue, this is the true parameter. This is really how everyone feels, except even though it's true, it's unknown. We don't really know where it lies. So we take our point estimate. So let's say I have point estimate for P hat 1. So P hat 1, here's my point estimate. Is it the same as my actual parameter? Well, no, it's clearly not the same as the parameter P. It's clearly off by a little bit. But when I create my confidence interval, when I take P hat and I go out on either side, my 1.96, well, what happens is that I do include my true parameter in that confidence interval. So somewhere in that interval lies my true parameter. However, like I just said, we don't know if we were necessarily accurate or not. If I took a different sample, P hat 2, and P hat 2 is over here, and again, it's not the same as my true parameter, just like P hat 1 was not the same as my true parameter. If I go and I create a confidence interval now, though, and I go out that 1.96 in either direction, what happens here is that it doesn't include P. My confidence interval here misses the true parameter. It's not included in my confidence interval. Now, here's, again, that big issue. I don't know whether I have one that works, like P hat 1, or one that does not work, like P hat 2. There is no way of ever knowing that. That confidence level just means that 95% of the time it'll work. That's my 95% confidence. That also means that 5% of the time it is not going to work, but we have no idea which it is. Now, when we talk about confidence, if I want to be more confident in my conclusion, though, I'm going to need a bigger interval and a bigger margin of error. Because again, it's unknown. If I want to make sure that I'm including my parameter, I need to make my interval bigger. The bigger my interval, the more confident I can be. And again, this is related to the normal curve and those areas and those probabilities. And there are different standard confidence levels. But in practice, you can actually choose any level you want, because each confidence level you pick is going to have a corresponding z-score. Just like when we did the normal curve, every area under the curve had associated z-scores. Every alpha, every area is also going to have associated z-scores or critical values. And again, the more confident we want, the bigger that z-score is going to have to be to encompass more of our data. To find z-scores for other critical values, then, well, we're actually going to do what we have already done before and what we know how to do, and we're going to use our inverse normal function on our calculator. The first thing to do, of course, is take our confidence level and figure out what alpha actually is. So 99% confidence means alpha is 0.01. And our inverse norm function, we're going to take that 0.01 and divide it by 2 for my area. Again, you could divide it by 2 first, or you can literally type in 0.01 divided by 2 in your calculator and it will work. But that becomes my area because I want the area in one of the tails. And then again, we want the standard normal curve. So mu is 0, sigma is 1. We type all that in and I get my critical value is, well, okay. It's going to tell you that it's negative 2.576 because it is going to give me the left-hand tail. Typically, though, we are not going to include the negative sign. There's no need to. We're just going to include the absolute value. And so, again, if you type this into your calculator, when you round it to 3 decimal places, we should get 2.576. Again, your calculator is going to put a negative sign in front of it. Just ignore that negative sign when you're actually writing the value down. We want just the absolute value of that critical value. So if I wanted to now construct a 99% confidence interval for the same data that 274 Americans out of 1,015 believe higher education to be affordable, again, p-hat hasn't changed. My standard error will not have changed. The only thing that will have changed is my z-score or my confidence level. So again, we had calculated p-hat before. We had calculated that standard error before. Those didn't change. I'm just taking those numbers from our last example. The only thing that changed now was my z-score. And so my margin of error is still my z-score times that standard error. So when I plug those numbers in now, again, my z-score has changed to 2.576. My standard error is still the same. When I multiply those two, here's my answer, 0.0358. That's my margin of error. Once we have my margin of error, we can, again, calculate my confidence interval. So my lower bound and my upper bound. Same idea, take the point estimate, 0.27, and subtract the margin of error, then add the margin of error. So here's my interval now between these two values. And my conclusion, with 99% confidence, the proportion of Americans who believe higher education is affordable is going to be, well, between my lower and my upper bound, between 0.2342 and 0.3058. Like I said, sometimes it makes more sense or is easier to understand if we convert those to percentages. So with 99% confidence, the percentage of Americans who believe higher education is affordable is between 23.42% and 30.58%. And notice now, when I increased my confidence level, these numbers got further apart. My interval is bigger. More confidence means a bigger interval. Of course, my conclusion can also go back to the point estimate. So With 99% confidence, the proportion of Americans who believe higher education is affordable is 0.27. Remember, that didn't change. But the margin of error is now 0.0358. Or as percentages, with 99% confidence, the percentage of Americans who believe higher education is affordable is 27%, with a margin of error of plus or minus 3.58%. So again, my margin of error got bigger because I had more confidence in my answer. Again, confidence. The only way we can be 100% confident in our answer is to state that the proportion is between 0 and 1. It doesn't matter what we're looking at. The only way to be 100% confidence is to say, well, it's somewhere between 0% and 100%. It's somewhere between nobody and everybody. That's the only way you could ever be 100% confident. To reiterate, that parameter P is going to exist before any polling even begins. And then whether or not our confidence interval contains our parameter depends solely on that sample statistic. The parameter exists, but whether or not our sample is representative, well, that depends only on the sample. And sometimes it will. Again, if I have 95% confidence, that means 95% of the time my method works. But there's always going to be that 5% of time where my method does not work, and there is no way of knowing whether or not we're in the 95% or the 5%. So again, that confidence level is in the method alone. And that can be really confusing at first. If I said I'm 95% confident in my answer, well, that has a connotation that's a little bit different than saying I'm 95% confident in the method. And so, again, just be really, really careful about understanding that distinction. So the examples we've done so far are for our sample proportions. If my data is in terms of sample means, meaning that I'm given quantitative data, meaning that the data I'm collecting is actually now numerical, I'm collecting numbers. My sample means they're not going to fit the normal curve perfectly, so I can't use my normal distribution. I need to use what's called the t-distribution. This is also sometimes called student's t-distribution, after a guy who used a fake name student to publish his works. So it's called the student's t-distribution, but has nothing to do with actually being a student. It's just more confusing. We're just going to call it the t-distribution. So the t-distribution is very similar to the normal curve. It has that same bell shape. It still has the mean in the middle. The only thing that is a little bit different is how much data is included. And that data that's included has to do with how big our sample size is. And what we're actually going to use, though, is our sample size minus 1. And we call that our degrees of freedom. And again, it has to do with how many different ways we can arrange things. The important thing to remember, though, is that our degrees of freedom, which is sometimes given as df, is really going to be n minus 1. And for sample means, we use t-scores instead of z-scores to find our margin of error. To find the t-scores, well, we're going to use the inverse t function on your calculator, which is actually right next to the inverse norm function on your calculator. Now, if your calculator does not have the inverse t function, and old calculators might not have this, TI calculators that are probably more than about 10 years old don't have this. I actually have a TI 83 calculator from 1997 that I got when they first came out when I was in high school, and it doesn't have it in there. In that case, you have to use the tables, and if you're in that group where you have to use the tables and your calculator is not going to give you that value, send me an email, let me know, and I can go through how to read the tables. It's really not that difficult, but hopefully most of us can use technology and the calculators to do this. So how do I find the t-score associated with, let's say, a 96% confidence and our sample size is 18? Because again, the t-score is now going to depend upon my sample size. Well, if we go to the inverse t function on your calculator, well, the first thing to, again, kind of do is convert our confidence level into an alpha. So 96% confidence, that complement is going to be 4%, and then convert it to a decimal, so 0.04 for alpha. And then the inverse t is going to ask for the area. The area is always going to be alpha over 2. So just type in 0.04 divided by 2. df stands for our degrees of freedom. So if our sample size is 18, our degrees of freedom is going to be 17, because that's going to be 18 take away 1. And then just hit enter. And we should find that your calculator spits out this t-score, which is our critical value now, of 2.224. Let's try that one more time with a different confidence level and a different sample size. So if I want the t-score associated with 88% confidence and a sample size of 35, convert the confidence to an alpha. So again, complements, my alpha would be 12%, which is 0.12. The area in this case is then going to be the 0.12 divided by 2. It's always alpha divided by 2. The degrees of freedom, well, what's 35 take away 1? 34. Enter, enter, and my critical value becomes 1.595. All right, that's how we find our t-scores. So let's actually do a bigger example, like a whole example of finding our confidence intervals. So a consumer protection agency is testing the average battery life on a new iPhone. So they take 30 phones to test, and they find that they have a mean battery life of 8.3 hours of talk time with a standard deviation of 2.7 hours. And we want to construct a 99% confidence interval for this data. Now, sometimes you're not going to necessarily be given the mean or the standard deviation. You'll be given a data set, but again, use the stuff we learned back in Chapter 3 to find that sample standard deviation and to find that sample mean. So again, the first thing I did was just try to organize the data. So my sample size is 30 because we tested 30 phones. My sample mean, X bar, is 8.3. And my sample standard deviation is 2.7. Now, notice again, it is a sample standard deviation, not a population standard deviation, because, well, again, we're only looking at a small sample of phones. So make sure if you're using technology that you're using S. Now, the first step with any data set, if we're doing this professionally, although again, my math lab might not ask you to do this, is to verify that the data is going to be independent and normal. Independent is the easy one because you just have to be less than 5% of the population. And again, clearly 30 iPhones are going to be less than 5% of all iPhones. The approximately normal is going to depend on whether we're dealing with a proportion or a mean. So remember, for sample means, to assure that it's approximately normal, we need to use our central limit theorem, which means that my sample size has to be bigger than or equal to 30. So, well, my sample size is 30. And so is 30 bigger than or equal to 30? Well, yeah, 30 equals 30. It's going to work. So we are approximately normal. We are independent. We can continue on with our analysis. Step 2, I want to find the margin of error based on the confidence level and the standard error. So again, this is all very similar to doing it with proportions. It's just that we need to use the t-score. And again, just like before, if I have 99% confidence, find my alpha level. So my alpha is 0.01. So when we use the inverse t function, it's 0.01 divided by 2. My degrees of freedom would be 29 because, again, take 1 away from my sample size, which is 30. And we find my t-score. And again, we're going to be using this to find our margin of error, so good idea to make a mark of it there. Because the next step is going to be to find our standard error, we need our formula for the standard error, which again is going to be a little bit different. Remember, this formula for my standard error comes from Chapter 8, where sigma sub x bar is equal to my sample standard deviation S divided by the square root of my sample size n. So my sample standard deviation was 2.7, my sample size was 30, so 2.7 divided by the square root of 30, and my standard error now is this value, 0.493, if I round it to 3 decimal places. Last up, my margin of error. My margin of error is the t-score times the standard error. Again, very, very similar to when we did the proportions. So we just plug in those numbers that we found. the 2.756 for the t-score, the 0.493 for my standard error, and I get 1.359. All right. Now, because I'm going to be doing my confidence interval around my point estimate, which was the 8.3 is my mean or my average, I'm going to round this one to 1 decimal place as well, just to make it a little bit more clean. Just pay attention to my math lab with how many decimal places they want for your final answer, and just, kind of be careful in that regards. Now that I have my margin of error, now I can actually build my confidence interval. And again, the confidence interval is just going to both sides of our point estimate. Now in this case, my point estimate is x bar because I'm dealing with a sample mean. And my sample mean is always x bar. And so I'm going to subtract my error and add my error to get my lower bound and my upper bound respectively. So 8.3 minus my 1.4 is 6.9, and then 8.3 plus 1.4 is 9.7. So those are my bounds. Last up, I just need to write a conclusion for this. My conclusion needs to include my confidence level again. So with 99% confidence, the average battery life for an iPhone is between 6.9 and 9.7 hours of talk time. Again, that's my confidence interval. Or we could write it with the point estimate and the margin of error. With 99% confidence, the average battery life for an iPhone is 8.3 hours, and my margin of error was 1.4 hours. The last topic I really want to talk about with confidence intervals is sample sizes. So our sample size is going to affect our margin of error. As our sample size increases, our margin of error is going to decrease. This is that law of large numbers, or what's called the wisdom of the crowd. And if I have a bigger sample, my data should be more accurate. So my error should be smaller. Now, if you're doing professional research, you need to determine what your confidence level and your margin of error is going to be before you ever begin your study or your experiment. You're not allowed to just collect data and then hopefully it will work, because that also leads an incentive for researchers to collect their data and then, well, honestly, kind of fudge the numbers a little bit to make it work so that they will be able to publish. So the accepted procedure is to start off with what is your study, what is your confidence level going to be, what is your margin of error going to be, and then we can actually use some algebra to figure out how big your sample size must be. So for sample proportions, we know that our margin of error was our z-score times our standard error. And if I plug in my formula for the standard area, or standard error, this is what we get. Now, it's not too difficult to do a little bit of algebra to solve for our sample size n. And if you feel like doing some algebra, feel free to derive this on your own. I'm just going to give you the formula here that my sample size ends up being p times 1 minus p times the quantity of my z-score divided by the margin of error squared. And again, that's a fairly important formula that you're going to need for your homework, so you probably want to make a note of that. But if I don't know what p is, because, well, if I haven't actually done the research yet, I don't know what my proportion is going to be, we have to just assume it's a coin flip. We assume that it's going to be 0.5, that it's a 50-50 shot for our proportion. So for example, a researcher wants to study the proportion of people who would like stricter gun control laws. The researcher knows that she wants her study to have a 90% confidence level, and her estimate needs to be within 3.5% of the parameter. Determine the sample size that she's going to need. Well, again, start with the confidence level. 90% confidence. What's my alpha? Well, my alpha is 10%, or 0.1. And we need to find our z-score that is associated with that. So the inverse norm of, well, my area is the 0.1 divided by 2. Mu is 0, sigma is 1. That's our standard. And so our z-score is 1.645. So again, we're going to need that value And then the other part is my margin of error. So the word within is going to indicate to you what your error actually is. All right, that within means your margin of error. Now in this case, they gave my margin of error E as a percentage, which means when I actually do the math, I'm going to need to convert that to a decimal. I need to move that decimal place over 2 spots. So my margin of error E is actually going to be 0.035. Now, if a previous study showed that 42% of the population was in favor of having stricter gun control laws, well then P is 0.42. I have my formula that we just gave a minute ago, and then it's just a matter of plugging all the numbers in and doing the order of operations correctly. So again, be careful. Practice doing this on your calculator. Make sure you pause and follow along and make sure you're getting the same answer that I am. If you need to, remember, do division first, then do exponents, then do the multiplication. But again, you should end up with approximately 538.1124. Now here's the thing with sample sizes. We need to guarantee that our sample is going to work. So we always, always, always have to round up, no matter what. I know typically, because this ends in a 0.1, we would round down, but with sample sizes, we always, always, always have to round up, which means they would need 539 people in the study. Now, what if there was no previous data to use? What if there was no previous parameter for this problem? Well, if there's no previous data, then we just use 0.5. We assume that the proportion is a coin flip. It's that 50-50 chance, so we use 0.5. Same formula, still plug everything in the same way. And in this case, I got 552.25. Again, take your time. Check to make sure you're getting the same numbers as I am. We always round up, so you need 553 people in the study in this case. For sample means, it's fairly similar. We're just using slightly different formulas. So for sample means, my margin of error was my t-score times that standard error. And my standard error was found this way. And so again, what I want to do is try to use algebra to solve for n, which again isn't terribly difficult, but might as well give it to you for free. And so my sample size is going to be my t-score times s over e all squared, except I can't know the t-score without my sample size. Right? My sample size determines my degrees of freedom, which is necessary for my t-score. So because I don't know what that's going to be, I'm going to need to use my z-score instead. And so to find the sample size, even for sample means, we have to use the z-score. All right. So our last example. A researcher wants to find the average amount families spend on groceries in a week. He wants a 95% confidence level with a margin of error of $25. A previous study had found a standard deviation of $75. So how many families must be a part of the study? Well, as usual, let's start with the confidence level. If I want to be 95% confident, that means my alpha is 0.05. And we had actually already done this one. We know that the z-score for 95% confidence is 1.96. I mean, that's something that you could probably even go ahead and memorize at this point because it shows up so often with our statistical inference. We also know that the margin of error is going to be $25 because that's given in the problem. And we're given that the sample standard deviation of a previous sample was $75. Now we have everything. Now that we have everything we need, well, it's just a matter of plugging it into our formula for the sample size and making sure that we follow the order of operations and we get the correct answer. So in this case, my sample size ends up being 34.5744, which means I need to round it up to 35, and they would need 35 families for their study. All right, I know this is a lot of information, and that confidence intervals can be a little confusing at first. All you need to do to get good at this, though, is to practice the process. Do the homework, and if you're still a little confused, if you still can't do that process with the homework, without having to kind of go back to the notes and work out a few times, just keep practicing. I promise that the more you do this, it's the same steps over and over again, and it'll get easier and easier. But if you do have any questions whatsoever, please don't hesitate to email me, and good luck studying.